fully turbulent steady flow of 250 cubic feet per second passes through a 1,000 foot long, 6 foot diameter pipe with an F1 of 0.012, and then through a 250 foot long, 4.5 diameter pipe. If the friction head loss in pipe 2 is 3 feet greater than that in pipe 1, where H2 equals H1 plus 3 feet, determine the Darcy-Weisbach friction factor F2 for the second pipe, and neglect minor losses. So this problem is very direct in that it tells you that it's looking for the Darcy-Weisbach friction factor F2 for the second pipe. So searching for that in the reference manual will lead us to section 6.3.2, where we can write out the equation. But first, in case you need a visual, this is basically what the pipe structure looks like according to the problem. So if we write out our knowns, we can see that Q equals 250 cubic feet per second, D1 equals 6 feet, L1 equals 1,000 feet, and F1 is 0.012. These are all for pipe 1. For pipe 2, D2 equals 4.5 feet, L2 equals 250 feet, and we are solving for F2 in this problem. So, let's write out the Darcy-Weisbach equation and see what we've got so far. This equation is going to be HF equals F1 times L1 over D1 times V1 squared over 2G equals F2 equals L2 over D2 V2 squared over 2G. Now, most of our values have been given already, but what we can see is that we are missing velocity for both pipe 1 and pipe 2 right now. However, we do have what we need to solve for those, so let's do that first. So velocity is going to be given by Q equals VA. So if we have our A's, we don't have our areas yet, but we can calculate those in turn from our diameters. So A1 equals pi d squared over 4, which will be pi 6 feet squared over 4, equals 28.26 square feet. Area 2 will be pi times 4.5 squared over 4, will give us 15.9. So now that we have our areas, let's solve for V1. If V1 equals Q over A1, then that's going to be 250 cubic feet per second over 28.26 square feet. And this will come out to 8.84 feet per second. Likewise, velocity 2 is going to be equal to Q over A2. The Q is the same since it's constant through both pipes, and this will come out to about 15.92 feet per second. So now that we have everything we need for the Darcy-Weisbach equation, let's narrow down exactly what H2 and H1 are equal to. So if we start by solving for just H1, we can write out just half of the equation, stating that H1 equals F1 times L1 over D1 times V1 squared over 2G. Plugging in all of these terms, we can see that F1 is going to be 0.012, L1 is 1,000 feet, D1 is 6 feet, V2 is our recently calculated 8.84 feet per second squared, and then 2 times gravity of 32.2 feet per second squared. Solving this out, we get an H1 of 2.43 feet. Likewise, this will mean that H2 is going to be 2.43 plus 3, giving us 5.43 feet. So now we have everything we need to solve for the F2 value in the Darcy-Weisbach friction factor equation. So in the same way that we recently solved for H1, we can now set H2 as our known and back calculate for the missing F2 value. So plugging in our terms, we have 5.43 feet equals F2 times 250 feet over 4.5 feet times 15.7 feet per second over 2 times 32.2 feet per second squared. And if we rearrange the unknowns and knowns here, we can isolate F2 and find that it is equal to 0.025, which is our third answer on the left. So this problem can be confusing just because there's a few steps you have to solve for before you get the value you're actually being asked to find. So again, we start by finding our velocities because those are terms that are missing from the Darcy-Weisbach equation. Then we use that to find our H1 and then subsequently our H2 values, and from there we can use all of that to find our F2 value. And that's it.